Welcome to this video series on frequently asked questions about the Java language. In this ongoing series of videos, we'll answer commonly asked questions about the Java language. You'll come away from the video with a solution to a question that you as a developer may have. In fact, these questions have been asked by thousands of developers, so you're not alone. Our approach to every question is simple. First, we pose the question about the Java language, Java development, or best practices. Then we fill in any background material so the question makes sense. Next, we'll get into the details of the question and discuss it further. Then we come up with an answer. As a bonus, we'll go deeper on the answer and look at a code example showing you what to do and in some cases what not to do with a counterexample. Stick around until the end of every video where we'll discuss the solution from an application security point of view. We'll let you know what you want to watch out for to ensure your code stays secure. For more videos like this, like and subscribe to be among the first to know when we release something new. Ready to get started? Let's go. So the question we address in this video is, why is processing a sorted array faster than processing an unsorted array? First, let's understand what prompts the question. Let's say that we generate some random data in an array. Then we perform some long-running operation on the data. In the example we'll see later, we'll sum the data thousands of times. In one case, we'll sort the data before the long-running operation, and in the other case, we'll leave the data unsorted. Then we'll add a timer to see how much time it takes to process the two sets of data. The time taken to process the sorted array will go much faster than the unsorted array. Depending on the language, the time can sometimes be dramatic. So the question is, why does this happen? When the situation occurs, and it may not occur for every language, it's because the compiler and the underlying CPU are making use of a technique called branch prediction. Branch prediction speeds up the processing of branch instructions in the CPU by reducing the costs or the time associated with branching. Consider the if statement we see here. If the processor sees a decision point like this or a branch, it has no way to know which path to take. The CPU could halt execution and wait for the instruction to execute, or it can continue on with processing, anticipating that it made the right decision. Modern processors have long pipelines of instructions that are designed to continue processing. To aid in this, if it guesses right on the branch decision point, it never has to stop. But if it guesses wrong, it will stop, roll back the transaction, and restart to take another branch. By sorting the data ahead of time, it allows the processor to take a branch again and again and never have to roll back and restart, and to gain tremendous efficiency when processing the data that takes the predicted path. Even though the underlying CPU might have this capability, not all compilers are able to take advantage of it, which is why some languages will not see much of an improvement by sorting the data before processing. So the key is the decision points in your code. If properly optimized, the true path may have a slight performance increase if it's taken most often. This will be most obvious in computationally complex processing. There are other optimizations that can be made as well using the ternary operator. The underlying instructions that are generated may be slightly more efficient than a conventional if-else statement. Now let's take a look at some code. I have a project set up in IntelliJ IDEA running on Windows 10. Let's start by creating a class with IntelliJ. We'll call it Array Processing Unsorted. Let's close the project panel so we get more real estate on the screen. Rather than watching me type a bunch of code, I'm going to copy and paste the code into the class and we'll walk through it. It's fairly short and everything is contained in the main method. Before we look at the code, let's fix the import statements. We'll click and select Import, so java.util.random is added to the import statement. In the top section, we create an int variable that determines the size of the array that we'll create and call it array size. It's assigned a value of 32,768. Then we'll create an int array of that size. In the next section, create a variable called random of type random We pass an argument to the constructor so that we get the same set of random values on each run. Then we loop through the array, and for each element of the array, we assign it a random value mod 256. Next, we get the start time and record it. We initialize the variable sum to 0, which will hold our result. And we simply loop for 100,000 times. Inside the loop, we run an inner loop over the entire size of the array we created earlier. And we have a conditional statement. The data element in the array is greater than or equal to 128, then we add it to sum. Else, we implicitly do nothing. And that's it. Then we print the current time minus the start time, which will be the elapsed time, and divide it so that we get back seconds and fractions of seconds as a result. And then we print out the result to make sure we get the same value on each run. Remember, we're not optimizing for speed. In fact, we're really optimizing for slow, because we want this to take a long time and for the decision point on line 24 to be repeated again and again. So let's run the code. Notice that after it starts, then we need to wait for the processing to be completed. And when it's finished, we see that it took 13.57 seconds. All right, so this is our control. Let's see if by sorting the data, we can beat the control. We create a new class called Array Processing Sorted. And once again, to save typing, I will paste in the code. Let's first fix up the import statements by importing java.util.arrays and java.util.random once again. The only change made in the code was the addition of the arrays.sort array data on line 18. But rather than taking my word for it, let's use a nice feature of IntelliJ to verify that. We'll go back to the project pane, select both files, right-click, and go down and select Compare Files. Now we can see the two files side by side. We see that the import statement on line 3 of the Array Processing Sorted class is different, as is the calls to arrays.sort on line 18 of that same file. Otherwise, the code is the same. Let's close the comparison file and run the Arrays Processing Sorted class. And wow, what a difference. This code runs in 6.2 seconds, more than twice as fast. Notice that the sum is the same as we saw in the previous code. Just that small change in the code made a huge difference, and clearly, Java is taking advantage of the optimization. So, are there any security concerns around this topic? There are no security concerns around the optimization of your code in this way, as long as you practice a security and testing first mindset. Make sure your code behaves well and passes all the behavior, acceptance, and security tests that you create for it. You are creating them, right? Although that may not be popular with developers, negative tests are important since they can help you discover how an application may break by using it in an unexpected way. Don't always assume the happy path. Hackers certainly don't. And if you do heavily optimize your code, make sure it still performs the necessary work and you get the expected outcome. Thanks for watching. We hope you enjoyed this video. Please like, subscribe, and share this video with others. To get our free ebook on how to write more secure Java code, go to www.beginsecuretraining.com. When writing code, remember to always begin secure.